This video covers force on wires in an external magnetic field. For us, current-carrying wires are magnets. So if a current-carrying wire is running through an external magnetic field, meaning a field caused by another magnet, then the two magnets will interact. The external magnetic field will put a force on the current-carrying wire. Now, to solve for this force, we have to have the current times the length of our wire times the magnetic field, and this is the external magnetic field. Okay, this is the magnetic field produced by the external magnet. That's one of the most important parts here. And then theta is the angle between the wire and the magnetic field. Again, remember the external magnet is a completely different magnet. That's where the magnetic field is coming from, and is not part of the wire. It actually pushes on the wire, which is a second magnet. Now on the left, what we have is a picture of what we've seen before. If we have a wire that carries a current, it produces its own magnetic field. That's what we refer to a wire carrying current as a magnet. On the right-hand side, this is a wire that carries current in an external magnetic field. What that means is there's a magnetic field already produced there, and then this wire is just running through it. But because these two are different magnetic fields, they're actually going to interact. And the way we can calculate that one is through this new equation. Now remember, by convention, the direction of current is the direction of the moving positive charges in a current-carrying wire. So when charges enter a magnetic field, they are forced to change direction. Whatever happens to the charges in the wire happens to the wire. The charges in the wire are forced upward, so the entire wire is forced upward. The wire actually jumps upward with this force. Again, ILB sine theta. This particular device is called an electric motor. Now here we're asked to determine the direction of the force on the current-carrying wire that have been placed in an external magnetic field. Again, these are current-carrying wires, so this wire is coming out at you, so that's your thumb. It's in an external magnetic field, so we know that this particular wire produces its own magnetic field, which goes in this direction, but it's put into an external magnetic field. So again, thumb out at you, fingers going to the left, and then the force, your palm, going downward. Again, here we have a different current-carrying wire. Again, the wire is going into the page, and it's put in an external magnetic field that goes downward, so your fingers go down. Your fingers go down, and then the force, or your palm, will go to the left. So again, this is an example that we've already seen, that if we have a wire that carries current, what we see here are the magnetic field lines for this particular red wire right here. And then let's say that we have a positive charge going through this magnetic field, then we can actually solve for the force on that particular charge by using this equation. But again, now what we're doing is we're replacing that particular charge with a series of charges, meaning a current. But now we can no longer use that equation. We actually have to use our new equation here. So here we're given a problem. It says wire A carries a current of 1 amps and wire B carries a 2 amp current. The wires are 20 centimeters apart and they are 50 centimeters long. And we're asked to determine the force of wire A on wire B. Now for this part, we're going to ignore wire B and treat it as a point P. Next, we're going to draw the magnetic field of wire A. So again, our thumb goes up, our fingers curl around in this direction. That means the magnetic field goes into the page here and out of the page on the left-hand side. Now we need to solve for the strength of the magnetic field of wire A. So to do that, we need to do B is equal to mu naught I over 2 pi r, where r is the distance between wire A and wire B. Remember, this equation can also be written as 2 times 10 to the negative 7, and that's combining all these constants up in front, and that's I over r. So 2 times 10 to the negative 7 times our current of wire A, so that's 1, divided by the distance between them. Again, they're 20 centimeters apart, or 0.2 meters. Gives us a value of 1 times 10 to the negative 6 Tesla. and this is going in the negative z direction. Again, we just solved for the magnetic field produced by wire A. So now that we know the strength of the field at point P, now we can solve for the force on wire B. So, to do that, we simply use our new equation, which is ILB sine theta. In this case, they are already perpendicular to each other, so that means we just need to use the current of wire B. So that is 2 amps. The length of wire B is 50 centimeters long, so that's 0.5 meters. And the magnetic field is 1 times 10 to the negative 7. So that means that the force acting on wire B is 1 times 10 to the negative 6, and this is a force, so we're dealing in newtons. Again, the direction of this force comes from the right-hand rule. So that means if my wire is going this way, then that's the direction of V, and then it's put into an external magnetic field which goes into the page. That means my palm is going to go off to the right. Again, you can double check that with your right hand rules. So if it's going off to the right, that's a positive x direction. And then finally, we're asked to determine the force on wire B by wire A. Actually, I'm sorry, determine the force of wire B on wire A. But again, Newton's third law says that these forces must be equal and opposite. So the force is still just 1 times 10 to the negative 6. But now it's opposite in direction, so this now goes to the negative x direction.